Ferrites. Okay, what are ferrites? Ferrites are special devices used for suppressing unwanted noise interference, harmonic spikes on wiring, PCBs, or for that matter, used on any electronic unit device that you can think of. And by the law, okay, you will have to, if you're making any electronic device in today's environment and time, you will be sort of faced with the noise and interference to be able to comply, even for yourself, never mind for the manufacturer. So you do get what kind of a sort of ferrites? You get the toroid rings, you get the specialized for soldering in line with wires. You get the surface mount. You get tubular sort of ferrite rings, and just the rings on its own. Then, of course, you do get the clip-on ferrite sort of ferrites. And today's video is basically dedicated to the a clip-on ferrites, which I'm going to quickly demonstrate on my little setup, which you will see just now on a spectrum analyzer, that they do attenuate the signal, and they are very, very essential in today's environment and applications. Okay, not just a clip-on, all of them, but today we're doing a demo on the clip-on ones. And this is my little setup. Okay, basically, what I decided to use the little step up sort of from, you got the input basically from 9 volt, okay, and then gives you USB output 5 volt up to say 1 ampere output in this particular module, and it uses a switch mode power supply. So I decided, because they do generate lots of noise, okay, and I'm going to demonstrate actually how these ferrites, that you've seen on the picture just now, attenuate the noise anywhere from 0 to 100 megahertz. And I decided to use the real sort of world, not my generator to feed the signal. I'm going to use this particular module that generates plenty noise, very broad spectrum. And what I did is I basically attached it to the cable. I applied over here, basically 2.5 volt, and on the output I'm getting something like precise on the output. I'm getting precisely 5 volt, and then of course on the output over here off screen I got a little dummy load, which is approximately maybe 10 to 12 ohm. And now with the peg, what I basically did is I just sort of clipped it to my coaxial cable, which is actually connected to my two-way radio, you can see, okay? And of course on the other side the cable goes into fed into the antenna. So basically over here it's inductively coupled. Okay, so I decided with my special current antenna, I decided to just clip it on with a washing peg on top of the cable. Okay, in other words, there is no electrical connections, and measure the actual signal coming into this cable, which is because this particular sort of module that I got just clipped on, touching the actual coaxial wire, so it's no way electrically connected, inductively actually creates and induces the common mode noise and the differential noise into this cabling. So now with the very sensitive spectrum analyzer, I'm able, because I'm using 1-to-1 special current transformer, which are just, as I said, it's just touching the coaxial cable on the outer, in other words, not electrically coupled. But due to the very high sensitivity on the instrument, I'm able to measure the induced current on the outer shield of this particular cabling, yeah, on this RG58. In other words, I will display it in dBm, or I can display it in microvolts, dB microvolts, or just a microvolts and so on. But nonetheless, for today's exercise, I just want to demonstrate and show you on the screen that, yes, you will be able to suppress the actual signal on the actual wiring just by clipping this, what you call it. Now I'm just going to, let me just do it again. Okay, I'm just going to reset it and watch the signal now. Okay, I put it on maximum hold. Okay, let me just put it there. Okay, right now on the instrument you can actually see, let me just zoom a bit more. Okay, let me just do it that way. You can see I'm actually measuring from basically 3 megahertz to 100 kilohertz. Okay, let me see. Okay, 3 megahertz to 100 megahertz. That's basically the spectrum that I'm measuring. And you can see there is quite a bit of a noise over here. Very much so, okay. Although this unit, it's not electrically coupled to this coaxial cable, yeah, you know, you're still measuring, you know, the quite a substantial noise induced due to the common mode and differential sort of mode noise. So on that note, what I'm going to do is, you can see more or less, okay, where it is, and I'm going to take one clip on, and I'm just going to clip it on, okay, and now it's clipped basically, if you look at it, it's clipped somewhere in the center, okay. It should be actually closer to you or whatever, but doesn't matter. I'll just clip it in the center just for an exercise. And now I press reset, and then let's zoom and see what happens. Okay, right now, once it finds a peak of the actual induced voltage over here, it will lock on the top part in the instrument, and the instrument did lock. And look at it right now. All these big spikes, they have gone away. Now, if I want to introduce but more attenuation, what I'm gonna do is I'm gonna actually add now another one. Okay, let me just clip another one. Okay, there we go. Now it's clipped another one. Again, I'm gonna reset and watch now. It's even further attenuated. Okay, you can virtually see that signal just about disappeared, except in the lower portion of the, which is understandable. I'm also picking up, because remember, on the bench here, I got wiring all over the show. I got some spectrum analyzers, but further on, okay, not to move the camera, and the other instruments, which also generate noise. So the lower spectrum picks up that common mode noise, which gets inductively coupled. It has been reduced by adding the ferrites, but it's still present there in quite a sort of strong manner. Now let me again remove the actual, okay, let me just remove it, okay, and then you'll see again how the signal will increase, which is a proof that these things, they do work and they're essential, and you have to use them whether you like it or not in order to protect your electronic equipment. Okay, now I'm just going to reset it again and let it scan. Watch now. Look at it there. It's unbelievable how much, and yet this unit is nowhere electrically connected to the wiring, and this cable and the RJ58 has got a very good shielding, yet still picks it up, and it's induced into the actual wiring. Okay, for this particular purpose I use the coaxial cable, but it makes no difference whether you use a coaxial cable or you use the wiring, type of thing. The noise will be still present, probably even more, because it's not shielded, type of thing. So, okay, and now you can actually see, let me zoom again, you can actually see how much noise without the actual ferrite. Look at it. Okay, there is no ferrites. I removed it from here to there, basically. There is no ferrites. Okay, watch now. I'm going to reset again. Okay, let it. Okay, and I'm going to take. Okay, let me just clip it on. All right, now it's clipped on. Reset again and let it scan. You can automatically see how much less noise there is. Okay, now watch, I'm gonna clip another one. Again, I'm repeating the procedure for a second time. There we go. Now I clip, a reset. You can actually see there is virtually 90% of the unwanted noise has gone. Of course, this peaks in a very low frequency up to 3 megahertz. They are inductively and capacitively coupled, should I say, from my other instruments that surround the actual bench. Yeah, on that note, I hope I sort of explained well. And basically, in this video, as I said, was dedicated to the clip-on ferrites. And that's what they actually do in real world. And I used a real noise generator, which is all these little modules, step up or step down, basically modules. They're terrible for noise. So on that note, thank you for watching. Until next time on some other sort of ferrites demo.